5, 4, 3, 2, 1. Let's go. Okay. I'm going to put my timer on because I have 100 slides. And when it stops, class is over. Okay. So when it rings. So my name is Bertel. I'm from Copenhagen. I'm going to talk about the nested fixed point algorithm. That's like John Rust's way of estimating discrete choice models, dynamic discrete choice models with maximum likelihood. The idea is pretty simple. Just calculate the likelihood, maximize that guy. And then for every time you need to evaluate the likelihood function, you need to solve a fixed point problem. That's why it's like the nested fixed point problem. We're going to go through the details of that. And then later, we're going to try to estimate models of equilibrium, or where we'll try to search for prices that put supply equal to demand in various different markets. And that requires another set of constraints. And that's why we do like a doubly nested fixed point algorithm. So we're going to do it the brute force way. Anyway, so why don't we just get started? You heard about Harold Zucker already, like Bob told about this Mr. Zucker, the mysterious guy. This is a guy, okay? And he actually made it into the title of that original paper, the optimal replacement of GMZ bus engines and empirical model of Harold Zucker. That's the guy who was doing the maintenance and replacement decisions in this Madison company. And John, he modeled a guy as if he had like this infinite horizon problem, right? Because he was doing monthly replacements of or monthly maintenance decisions over a long life horizon. You can see, well, he passed away. It's not like infinite, but it's pretty long, because when the decision period is just 1 month. That was a pretty good start. Anyway, so that paper is about the first implementation of this nested fixed point algorithm. This is simple world of the engine replacement. That's like lots of different applications of dynamic discrete choice models that kind of, cite this work. And I'm not going to go through all this, but, there's so many different applications of, retirement and occupational choice, brand choice and advertising, route choice models, fertility and labor decision we just seen, and then this model I'm going to talk about at the end, which is joint work with Ken Gillingham and Fedor and Anders Mogh-Nielsen, John Rust, and who else? Who did I forget? Myself. Huh? Okay, and so we're going to end with that. Okay, and many more, of course. And here's a little. We call it the Big Mac Index of Dynamic Structural Econometrics. It's the citation count of the Rust 1987 paper. I kind of stopped updating here because it got a pretty good fit, an R squared of 0.999. So you can just, that's a structural relationship, right? Just use those parameters. I think we're around 3,000 sites now. So, anyway, that's a paper we're basing stuff on. So here's a model. The bus engine replacement model, simple binary response, 0, 1. 1 if you're replacing the engine, 0 if you're not. Okay, so just like Bob told us. And then we have these two sets of state variables. We're going to decompose into what is observed, X, and to what is only observed by Harold Zucker, these epsilons. Okay, and these are going to be taste shifters or idiosyncratic shocks to investment in engines, if you will. And they're going to be specific to the decision. And of course, if you have more decisions, or more discrete choices, it's going to be 1 for each of these alternatives. Okay? And so then we have like a payoff function or a utility function, which is additively separable in those observed state variables X, and then those unobserved state variables. And here's a functional form for this particular model. Now, if you keep the engine, don't do any replacement, utility is going to be negative with the cost of maintaining that bus, okay? And that might be increasing in the age of the bus. Okay? We think that, older buses, they get into trouble all the time, right? Because now it's another gasket that's blowing. So that's, we might think this is like an increasing function. And we want to estimate the parameters of that parametric function. So we're going to assume the parametric form for C and then try to see if we can estimate theta 1. So this can be like a linear function. Okay, we'll just estimate one parameter. And then if you replace, well, you pay the replacement cost, and then of course, like a cost of a brand new maintenance cost of a brand new bus. Now that's just for this period, of course. You do that every period. And so now the optimal choice of replacement is kind of weighing off the saved maintenance cost you have in the future, because you kind of regenerate that bus state to zero versus the cost of replacing now. So in order to make that optimal choice, Harold Sucker need to make expectations about how that future state is evolving. Okay? And you can control that partially by replacing the engine. Well, then the bus regenerates to zero. And then the distribution of mileage accumulated mileage on that bus engine is just going to be how much is driven since this morning or since the replacement. Otherwise, it's going to be determined from where it was. So it's like, think about just a random walk, right? And then sometimes, the current state is just multiplied with zero if you're replacing the engine. Okay, now that's a model, pretty much. And then we want to estimate the parameters that are indexing all these different parts of the model. Okay, so like the utility parameters, theta 1, and then the parameters that index in the state transition, theta 3 in this case, because we are normalizing the other parameters in here to later going to be ID extreme value. So that's the essential new parameter. Okay, so that's the model. Now, okay, so how do you make choices? You maximize the sum of current and discounted expected utility. And how to solve that problem? We solve the Bellman equation. Okay, so the Bellman equation is here, which gives the value, which is the max over all these many different choices, now to 0 and 1, of the sum of current and future expected utility. And then it's all about calculating that little expectation here, which is the expectation over the evolution of next period states, okay, given this period states and decision today, okay, we just solve this Doppler integral. Now, hey, that sounds pretty easy, right? But it's not necessarily, right? Because this x here, even just in this case with Harold Sucker, is a continuous variable. And they got continuous j-dimensional variable epsilon. So you need to like solve for a very high dimensional function. Because v is now a function of, I mean, that's the unknown of this equation. It's a function of x, and then this j-dimensional, variable x. So that's high dimensional. And then you need to take that expectation. Well, that requires high dimensional integration. Maybe we could do that with Monte Carlo or something, like for expressive dimensionality. But even so, we need to be able to evaluate the function we're integrating. So that's involves high dimensional integration and interpolation and whatnot. Maybe we can do neural nets today and everything is easy. But you see the problem, if you start just looking at the problem here, it's actually not a trivial problem. And then, of course, at the end here, this is a non-differentiable function with this value. Okay, so what can we do? We make assumptions. So we make some assumptions that makes our life easier. We've seen some of them already. Like first one, we're going to assume the utility is additively separable in the deterministic part of utility and this unobserved component of utility with these epsilons. Going to assume the conditional independence assumption, and Bob already talked about a lot about it. It means essentially that the state transition density for the joint states x and epsilon, okay, that factors into this two components. And what you should notice here is that, for example, the distribution of epsilons, once you condition on the x's in the same period, does not depend on the lag period of the epsilon. So it kind of rules out, like, for example, serial correlation. Now we can make additional assumptions about that distribution of the epsilon. For example, assume they are extreme value. Then we get like nice logit formulas and closed form for expected value functions. So we're going to put all this stuff together. And so here's the simplified Bellman equation. So it's the same as we had before here, but now kind of, decomposed a little bit here by imposing the conditional independence assumption. That allows us to essentially formulate the model so that we can separate out the deterministic parts of the choice specific values. As you can see right here, everything here until that epsilon footnote to the end does not depend on the epsilon, right? So it just depends on the x's, the observed states, and the decisions. So we're going to call that the choice specific value. And then we just have this little epsilon added at the end. So then that means once we've done that, we can easily express the Bellman equation in a much reduced space. Remember, we started with something like this, right? The value function, the solution to this equation was a function that was defined over both the observed state variables and this j-dimensional vector of unobserved states, the high-dimensional object. Now, what happened? What if we could just integrate that out and formulate the Bellman equation in expected value function space? Okay. Now, expected value functions, if we integrated out all those unobserved states, and we only need to condition on the state variables, x, the observed ones, then it doesn't depend on those epsilons anymore. And now this is a function only of x, the observed states like mileage, and then the decisions, the placement decision, much reduced space. And so we can do that and formulate the Bellman equation in expected value function space instead. And now you get like a mapping from expected value functions to expected value functions. See, here, these value functions, that depends on that future expected value. So how do you solve that? You could solve it by successive approximations. You start guessing an expected value function. You throw that into your Bellman operator, okay? And then that spits out an expected value function. So this is nice, right? First of all, it's a contraction. So this value function iteration or successive approximation is guaranteed to converge. Okay, if the beta, the discount factor is smaller than 1, it's just always going to work. Okay? So you get global convergence of value function iterations and successive approximations, and then that solution is much lower dimensional than what we started with. Now you can also do, we see that often, where we just, instead of calculating the expected value function, we calculate the integrated value function or the smooth value function, where we just take the expectation over the epsilons only and formulate the Bellman equation in that space instead. So that looks like this. Okay. So now we'll have we call this the integrated value function. Essentially, the expectation of the value function is only conditional on the current value of the states. Okay, and then we can, because of the conditional independence assumption, we can express this the Bellman equation in this much reduced function space. Okay. Now, I'm not expecting you to get all these little details here. I'm just saying, we started with something that appeared to be impossible, and then we made a few assumptions, and then we can then solve the model on a much reduced space, and we get the same thing out. Okay, this alternative Bowman operator, well, that's also a contraction, and you can find the unique fixed point, the value function that satisfies the Bellman equations by successful approximations again, or value function arrays. And it's just always congruent. Okay, and so it's even lower dimensional doesn't even depend on decisions. Okay, so that was 1 and 2. Now this last thing is I at extreme value. We still need to compute that integral here, right? That integral here. The benefit of that, assuming those at extreme value shocks, is that now that expectation of the integrated value function, that can be expressed in closed form. That's like an expectation. What is it? It's like an expectation of the max over all those alternatives, all those choice alternatives that there are, conditional on the states. That turns out, instead of being like an integral over all those continuous states that you need to like numerically approximate, we can just do this simple formula, the log sum. So that's another benefit of that assumption. So it rules out serial correlation, and it poses a particular functional form for the distribution of the epsilons, but it's really giving us something. Right? I mean, think about the alternatives. Calculating that j-dimensional integral with numerical integration over for this j dimensions, that's pretty numerically hard thing to do. Another thing it gives us is that the conditional choice probabilities, they have closed form logit expressions. So it looks like this, simple formula. Now we're in business, right? Because we can always express this expectation of the max as this log sum and the choice probabilities in simple logit expressions. Okay, so let's put this together. So we put all this together. Now we have an expression for the conditional choice probabilities. They're just logit formulas. And look at that little baby here. This is like the fixed point on the Bellman equation, that expected value function. So in order to compute those choice probabilities, we need to be able to compute that fixed point on this Bellman equation. You could do it, for example, by successful approximation. Here I'm putting a little sub theta here because the fixed point here is really an implicit function of the structural parameters, right? Because every time you change the structural parameters, you're going to change the utilities. You're going to change the way we take expectations through the state transition densities. So it's going to affect the right-hand side of the Bellman equation, and therefore also the fixed point, right? The solution going to change. So that's why we put a little subscript theta here to kind of emphasize its dependence on the structural parameters that we want to estimate. Okay, now we discretize the Smiley. So, I mean, you could deal with the continuous Smiley state in many ways. You know, you could parameterize the value function with Chebyshev polynomials or splines and neural nets or whatever. We're just going to discretize the whole thing, making it easy, because that's what John did in 1987. And so once you discretize the states, which is Myrick in this case, since replacement, we also discretize the distribution and becomes a finite state Markov process. So the distribution, the state transition process is just governed by these matrices of here's the probability, the Markov transition matrix. If you keep the engine, here's if you replace. So if you keep the engine, then with some probability you stay in the same state. This is if a person has a brand new bus, right? And with some other probability, you kind of move up the ladder, right? Because the bus is driving forward. Okay. And it's kind of opera-triangular, right? Why is it opera-triangular? I mean, this is like for an older bus, right? But keep the engine here. There's zeros over here, right? Below the same state. Why do you think that's the case? Then you would have to kind of or like drive the bus backwards maybe. Like work with the autonomy. Some people are doing that, but Harold Sucker is a very honest guy. Okay, he's not cheating. The only way he's moving back the mileage is if he's replacing the engine. Okay, and then it becomes as good as new. Okay, so we can just write this whole thing in matrix form, either the expected value function space or the integrated value function space. And now let's take this guy here, right? We know this is a log of the sum of the exponentials of the choice-specific value functions that we can write in this simple way here. And then how do you get the expectation over the mileage state, the integration over the mileage? Well, we are just multiplying with these macro transition matrices for all the different choices. Okay. Yeah. Well, you can think, okay, so here's a question. Why would we want to use, what is the cutback of, or what is the benefit of doing a continuous approximation compared to discretizing the whole thing? Well, first of all, this is easy, right? And everybody can see what's going on. The alternative is, of course, if you were to approximate this with a polynomial and just treating that continuous variable as continuous, you in the end you would have to at some point evaluate the function at some grid points. Right? And so let's suppose that we're using like 90 grid points, 90 intervals. So it's pretty hungry if you want to do like a nice approximation. Whereas with 90 grid points on Chebyshev polynomials, you can get pretty far, right? So you could actually reduce some of that computational complexity by making a parametric approximation. For example, if you have like 10 grid points and you can approximate, or let's say 11 grid points, and you could approximate that expected value function with a 10-degree polynomial, which is super flexible. You don't need more than that. And then you have represented the problem on something that's even more reduced, like only 10 points instead of well, what's the problem? It's hungry for grid points. You can think of discretization really as a parametric approximation with a step function, okay? Where you have like a spline, a zero-order spline that you just divide the state space into a bunch of different intervals, one corresponding to each grid point. And maybe that's, if you think that value function is really smooth, why don't you use something that's more smooth and exploit that. Anyway, so that's not a point I want to make here. I just want to say we can solve it, and we can solve it use Chebyshev polynomials or linear approximations or something flexible. So once we have that, we want to estimate the model. Okay, so we get data on panel data, for example, or on replacement decisions or discrete choices, and then the observed state variable mileage. You don't really need to have panel data. You just need to have the observations of the states in this period and the period before. Okay, so you can estimate the transition and then combined with the decision. Now, with that, we can formulate a likelihood. And so what's a likelihood? Well, that's the sum of the likelihood, log of the likelihood of all the conditional choice probabilities. Those we just computed here. Okay, all those logit formulas, but now evaluated at the data, of course. So it's that's the likelihood. And then we have a likelihood contribution for the state transition process as well. Now, the issue is, of course, that likelihood depends on the on the expected value functions or the integrated value functions, which in turn depends on the parameters because they're implicit functions. So every time, if you were to maximize this guy with respect to theta, you have to keep in mind, you also have to change the fixed point every time, like recompute the solution to this equation. Recompute the fixed point. Okay, and that's a nested fixed point. So essentially, in the infinite horizon case, since this Bellman operator is a contraction mapping, then the fixed point to this constraint is an implicit function of these structural parameters. And since everything is nice and continuous, you just move those around, those parameters, and then the expected value function changes continuously. So if you do that, you can formulate the maximum likelihood problem to an unconstrained optimization problem where you just maximize the likelihood function with respect to theta, changing the structural parameters, how they appear here, right? But also recomputing this expected value function. And so John, he talks about this like this outer hill climbing algorithm, search over the parameter space. Okay? And then you'll need some algorithm like Berndt-Hausmann's algorithm or BFGS or some other algorithms that search over the parameter space. But each evaluation requires a solution of the fixed point or the Bellman equation. So Bob did not talk much about that, right? He would just go out and observe in the data those conditional choice probabilities and add that to these corrections in the likelihood function. So nothing about like repeatedly solving, which is like a huge benefit of doing the CCP type of estimation. Well, we're going to do the hard thing here. We're going to solve repeatedly solve for the fixed point every time we change the parameters to implement the maximum likelihood estimate. So the way to do it is a combination of what we talked about already, like successive approximations or value function iterations, and then Newton-Kantorovich iterations. You can solve this problem here, this fixed point problem. That's just a set of equations. You can also solve that with Newton's stuff. I'm going to return to that. Turns out to be a good thing to combine these two ideas. Okay, so given all that, we can now estimate the model. Okay, so we have some structural parameters, and what John did in 1987, he estimated both a dynamic model and a static model. He will assume he knew the discount factor of Harrell-Sarkar, and he estimated he shows it to be 0.9999. So Harrell-Sarkar is very forward-looking. And this is like the other personality of Harrell-Sarkar, like counterfactual personality, where he's just looking at the engines, not worrying about tomorrow. Ah, yeah, why don't we just replace? Okay? So that's like they did in myopic model. So he estimated the model under these two sets of these two assumptions, and like different types of buses, like GMs and Fords and so on. And we grouped these buses into bus groups 1, 2, 3, 4, 5, and then he estimated the model separately for the two bus groups, and then together, and so you can, once you do that, then you just compare the log of the likelihoods for these two models. You can get like a test for if these two sets of parameters would be the same, stuff like that. Anyway, we can estimate the model. We can also do that in the code. And so that's what I'm gonna, in the repo, there's gonna be code for replicating Rust problem, okay? So there's both MATLAB code and Python code. I'm an old fart, so I'm gonna do MATLAB, okay? And so what you do is you just go into that directory. I call it's a Circa MATLAB directory. Okay, and there's a little README file. I'm not going to go through all that. You can kind of, I just want to show you the code is there. And it's called run bus data, and then kind of estimates them all. And then we have replicated the results. There's two ways to estimate the model. Here's one with like partial maximum likelihood, which is in the first step, we estimate the state transition process, just the Mile-Rich process, with just with regression essentially, and then we whole fix those parameters and estimate only the structure parameter entering into utility function. So that's RC, the replacement cost. In this case, it was a linear cost function. That parameter, the coefficient to that parameter there. Okay, so the utility or the cost will be C here times mileage. And then you can also estimate all these parameters jointly. So these are going to be all the thetas that enter into the state transition process. And so if you look at what we're estimating here, these are essentially the parameters down here. Anyway, I just wanted to say the code is there, the data is there. You know, it's a good way to actually learn how to do it. Just look at my code. How do you implement this? Okay, so then the models give different predictions. So here's the one for 0.999, the forward-looking hero circle. Here's the one for the static one. And here's the non-parametric hazard. Okay, this is like just taking that Mile-Rich, chopping it into bins. In this case, I think 90 bins. And you see, if you want to do like a frequency estimator with 90 bins on that original data, it gets pretty jiggery. Right? So, so that's one of the complications, one of the challenges of the CCP type estimators is you have to estimate that, those conditional choice probabilities from the data. But even here with like 8,000 observations, getting that non-parametrically potentially get you into some noise. You just use a frequency estimator. So what people do is, I guess, like a flexible load jitters. Okay, now that's the predictions from the model. The predicted probability of replacement. Now, once you have got that, along with the Mile-Rich transition process, you can actually predict what the Mile-Rich, how that's progressing over time. And you can calculate the equilibrium distribution of. And so that's what you can do with this model. Once you've got the conditional choice probabilities and the state transition, you can find the ergodic distribution to this state transition just by finding the fixed point of that equation. And that's going to be one, of course, for if you're replacing and one if you're not replacing. So they'll look like this. So here's the kind of the equilibrium Mile-Rich distribution from finding that solution. Given that equilibrium Mile-Rich distribution, that was just for one particular value of the replacement cost. But you can also calculate the demand curve from that by varying that replacement cost. So calculating, essentially using that distribution here, okay, using those distributions, you can calculate what is the expected annual engine replacement. Okay, and John has a formula. He multiplies by 12 months, and then he kind of integrates that. Okay, and now that you can do here for a particular value of the parameters, for one value of the replacement cost. So now we're going to recalculate that equilibrium distribution and that expected that expected annual engine replacement, which is like the demand for engines, by varying the replacement cost. Okay? And then these two models are going to have to predict it. So what you see here, it's actually that you get different predictions. Like the static model, it's much more elastic, right? It's like, it's not taking into the future that if I replace the engine, I'm going to have a brand new engine tomorrow. So it's going to be much more dependent on the engine. Okay, so that's Harold Zucker's model. So what we're going to do now is try to estimate it in a different way. And then later, we're going to estimate the model which have more choices and impose those equilibrium constraints from the model. Okay, so now we've heard about how to estimate with CCPs, with maximum likelihood, with the nested fixed point algorithm. But there's another approach, it's called mathematical programming with equilibrium constraints, that proposes to maximize the likelihood, not only with respect to the structure parameters, but now also with respect to all the different values of those expected values. Like we have a finite number of them because we have like discretized the state space into say 90 points. So we have like 90 additional variables. We could just treat them at 3 parameters and then make sure that the values, the expected values that we are choosing are satisfying the Bellman equation. So that's the same thing. So that's what Sue and Jacques propose. And it has some benefits because it's easy to formulate. You just write up this set of constraints and then the likelihood function as function of the expected value function parameters or variables. There's nothing about like constraint optimization, nothing about fixed point problems that needs to be solved and so on. You just let the solver do the job. Okay, they consider two such implementation. One in some high-level language called AMPL, if you know about like GAMS from the old days for solving general equilibrium models. That's similar. What it does is that it kind of formulates the problem as a constraint optimization problem, pass it to some state-of-the-art solver where engineers and computer scientists, they optimize that. And the benefit of that is you get like automatic differentiation. So you get like Jacobians of Hessians for the likelihood function, first and second order derivatives, and Jacobians of the constraints. All that differentiation you get essentially for free by automatic differentiation. Nowadays, you probably use like something like Python JAX, where you also have like 80 or automatic differentiation. So that's a nice thing, right? She also exploits sparsity patterns for the Jacobians and the Hessians. You take derivatives of the Bellman equations, and then it turns out to be very sparse. There's lots of zeros there, so you don't even have to consider those derivatives. And then there's a MATLAB implementation, which is where you have to like use the supply, the first order, second order derivatives. You have to like, write them down with pencil and paper, but in principle, you could do that. Sue and Jet did that, but then they did not supply the second order analytical derivatives. So anyways, they did a little Monte Carlo based on the Bosch engine replacement problem to make like a head-to-head comparison between NFXP and MPEG. Because you might ask, now these are two ways to attack the same problem. Both is going to be giving us maximum likelihood estimates. And it just sounds appealing that you don't have to like repeatedly solve all these fixed point problems, right? Just these constraints just have to hold at the end. Okay, so they did a little Monte Carlo, and they increased the fixed point dimension. That's the number of grid points to 197.5. And they assume here's the DEP maintenance cost function. It's linear, it's a one parameter. And then there's some parameters, the true parameter here is going to be 2.457. That's corresponding essentially to that for a set of parameters that we have estimated somewhere in John's paper. I think it's this one here. Yeah. So, okay, and replacement cost, 11.7, and then some parameters indexing the state transition. That's like these elements or that were all on the diagonal. The probabilities for staying in the same state is 10%, moving up one state is 44%, and so on. So that's a parameter. Now, given that set of parameters, we know like theta 1 and theta 3, we can solve for the expected value function at the true parameters. Calculate conditional choice probabilities, simulate the data, and that's what they did, like simulated 250 data sets of monthly data for 10 years and 50 buses, kind of to mimic the same type of data that John had. Okay, so here are the results. So what are we going to do? Is then NFXP like a dinosaur now? So we're going to compare MPAC in two different versions. This is the best one because it uses second order derivatives. So just focus on that one. And then we're going to compare to NFXP. And so we're going to do 5 runs with different starting values for each of these 250 Monte Carlo replications and count how many times it worked. And it looks like MPAC is working pretty good. And it's pretty fast, 0.1 second. And then it's counting how many major iterations. That's how many times it's essentially making an iteration on the Lagrangian. And then in order to do that, you need to calculate, make function evaluations that calculate the likelihood several times. And because we have first and second order derivatives, this is close to each other. And then sometimes you do a little bit of line searching, you evaluate the function more. But if you don't have the second order derivatives, then you end up using more. Then there's NFXP, not quite as stable. It's much slower, 24 seconds, because you repeatedly solve this again and again for every structural parameter. And then look at this, 134,000 contraction iterations to estimate this model. And it only gets worse, right? As you increase the discount factor, we get to 748,000 successive approximations. That's how many times you need to evaluate the Bellman operator. That's pretty time-consuming, and it takes more than 2 minutes. And then it's sick. Okay, holy cow, am I ever going to use NFXP again? And so there's still some hope. Okay, so I'm going to do a little bit of CPR. This is so the rest of this part of the talk is going to be about what do you need to do to make NFXP work? Okay, so you don't get into this situation. Let's I just did some. Okay, so first, read the documentation. Okay, so I went down, read the documentation manual of NFXP, and then there's some more tricks, and we're going to go through some of them. How am I doing? 45. Let's spend a little bit of time on this. Okay, now this is the CPR, right? 6 steps. Okay, you follow all these steps, and if NFXP heartbreak still weak, you do it again. Okay, because it's going to work. Okay, so here's some references, and actually this is version 6 of the NFXP manual. carefully describes essentially everything I'm talking about here. Yeah, of course, version 1 was in, I don't know, 1985, probably didn't change. And then we have a little comment here that also kind of highlights some of the things that were not quite right in the implementation of NFXP in the Sue geography. Okay, so here's a little bit from the documentation manual. So here's on page 18. It says, John says, formally one can view the nested fixed point algorithm as solving the following constraint optimization problem. Holy cow, what is that? That's MPET, right? So it's already there. So in that sense, that part is not new. The new thing here is the implementation in these state-of-the-art solvers, which is definitely valuable. So anyway, but John makes an argument why it's better to do the nested fixed point algorithm, because if you are treating this fixed point here as an implicit function of the structural parameters, and you can provably solve for those fixed point by successive approximation due to the contraction properties, you can also calculate the derivatives using the implicit function differentiation and get derivatives very get some derivatives. Anyway, so, and there's also a little map of how you get through the world of the nested fixed point algorithm. So you start here, right? You make a guess of the expected value function. You need to do that to get the value function iteration algorithm converging, right? Or starting. You need a starting place, like iterative algorithm. We just start with 0. And we're going to start with some parameters, parameter estimates, or some initial parameters. We need that for maximum likelihood. You know, it's also an iterative algorithm. So we're going to start with that. And then we're going to initialize we're going to do a contraction step. And then once you do that, you do a bunch of contraction steps. At some point, if you have what you put in, like the expected value is also what's come out, you have a fixed point, right? And then the question is, you're sufficiently close here, you get into like a domain of attraction, you can start to do Newton iterations. Anyway, that's what we're going to do. We're going to follow that map. Okay, now, in order to do that, there are some things that matters in terms of implementation here. For example, when you work with Logio formulas, you need to recenter it. What happens when beta goes high here? What happens to V? It becomes big, right? Because now we're discounting all those Harrow-Sucker utilities from his infinite future, putting weight on everything. It's just adding up a lot of numbers. That gives a big, very big number, right? Now you put that into the exponential, you get a very, very big number, okay? Now you divide by the sum of exponential, get like infinite divided by infinite, you just get overflow in the computer, okay? You don't have to think about that when you just work with the Greek letters. But once you implement things like this in the computer, you have to think about it. So don't forget that. And this is a simple way of recentering that. That's just say, these two are identical. If you were to take the max, V naught to be the max of all the different choices, okay? And you get the same choice probables, then all these numbers essentially become negative, and then you get underflow instead, right? Because exponentials of a negative number kind of bias towards 0. Like bias, but it's kind of, that goes towards 0. Now this is much more well. So, just look at your numbers on the computer. Because once these numbers get bigger, then you get into numerical. And the same thing here with the log sum. This log of the sum of those exponentials that were like very big numbers, well, that can also explode, right? But then you can subtract a value and add it outside. It's the same constant value. Okay, and which one is a good choice? Of course, it's going to be the it's going to be the maximum. Then you're sure that everything here is going to be negative. Anyway, so just think about that. Then, what about this successive approximations? Why are we not just, doing successive approximations all the time? Well, let's look at it. Okay, so here's a Bellman operator, and that's the iteration, right? You start with a guess on the expected value function. You put it into a Bellman equation. You get an updated version, okay? And then you just do it again and again and again and again. Okay, and because it's a contraction, it's always going to converge to the unique fixed point. And so here's the error bound. And what you'll see is it's linear convergent. And that rate of convergence is determined by the discount factor. So when that is close to 1, nothing happens. And that makes sense, right? We're trying to really approximate an infinite horizon problem with a finite horizon problem when you're doing successive approximations. So at some point, the future doesn't matter. But with beta equal to 0, future always matters. Okay, so it's going to take a lot of time for that to converge. So we might actually reformulate the problem here and find, instead of finding the fixed point of this operator, we're going to just find the zeros of this slightly modified operator f, which is just taking the Bellman operator and subtract on both sides, and then you get ED minus the Bellman operator. ED has to be equal to 0. Okay, so we'll try and solve this using Newton's method. That's the Newton Kantorovich iteration. So here you got the derivative of the Bellman operator, and this is just pure Newton, right? This is the function that we're trying to find zeros on, and this is the derivative of the function. And Newton is quadratic convergent. So that's pretty good. So here's what happens if you do successive approximations with a discount factor that's very close to 1, just like John had in 1987. Here's the tolerance. That's the maximum absolute difference between two successive approximations. That should be 0, right? Okay. You see, it's not quite 0, so we do another iteration. And not a lot of stuff happens. And after 50,000 iterations, well, we're closer to 0. But we really want this to be like at machine precision or something, right? Because you want to see how the solution that comes out of doing all these iterations changes when you modulate, we just changes parameters a little bit. Okay, now that might not change at all if you're not solving the model, right? Or change in a very lumpy way. Okay, so let's see. Let's see if we can actually do this. There's a little code here you can play around with. It's called run FXP. It's FXP without the N because it's not nested, right? That's doing the solution. Run FXP. Okay, and here I'm doing 100 successive approximations, and you see, okay, it's not quite there. We could do more. Just change the number of iterations. Let's do how many? Let's minimum do like 100,000. It might be converged by that. It takes a little bit of time. Oh my God, I did too many. Okay, there we go. Okay, so it does actually converge, but to that tolerance, yeah. That was a lot of iterations. Okay, so we could do instead, we can do this Newton Kantorovich iteration combined with, oh my God, that was not intentional. Okay, I'll just go back to the slides where we, in the first step, do all these successive approximations to kind of get a ballpark solution, and then we start doing the successive approximation, or the Newton unit. Here's the error bound, as you'll see, as a function of the iteration count. Okay, that was that number here. Okay, I just plot that against the iteration count. I do that for different discount factors. And you can see if the discount factor is 0.95, it goes very quickly. If it's closer to 1, it goes very slowly. Okay? And if you take the log of the error bound, you really see the linear convergence. Okay, the slope of these coefficients is going to be beta minus 1. So with beta very close to 1, the slope is going to be flat and nothing happens. Now, if you do instead the Newton-Kontorovich iterations, well, look at the tolerance here, 0.01, that's after 1. And then it's really 10 to the power of minus 2, at the order of 10 to the power of minus 2, 10 to the power of order 10 to the power of minus 4, and minus 8, and then you go at machine precision, right? So it's like you take the maximum approximation error to the power of 2. Okay, so this is where you see the quadratic conversions. If you take the log of the error bound and plot against the iteration count. So here I'm doing a couple of successive approximations, but here is the first Newton iteration. Next one, and next one, and they're all following this quadratic. So when to switch? See, the problem with Newton is that it's never really globally convergent. You have to kind of get into some domain of attraction. Well, what you can see here is that if you have already recovered the shape of the expected value function, and there's only a constant left, then that's going to be swithed away by Newton. So let's just assume that that's the case. Okay? So suppose that our initial guess of the expected value function is the true expected value function just plus a constant. Okay? And now I'm going to do successive approximations. Just throw that into the Bellman operator, and then you get this, okay? You move a little bit around, and then you get 1 minus beta times that constant. Okay? Of course, if beta is equal to 1, yeah, it's not going to be much of a change. We can do it again. That's like another iteration. Now I'm going to start from this expected value function I get out of doing one iteration more. And so I'm going to put that in. So this is just expected value times discount vector times that constant. All right? That's after one iteration. That's what we just learned. This is what we have here. And then I do it again. And then you get beta times 1 minus beta times that constant. Now you take the ratio of these two, that relative tolerance, you get exactly beta. Okay. Where did you see this before? Oh my God. These are the relative tolerance already computed. So once you see that, it's kind of a sign you recover the shape of the value function. It is just this constant left. So if you see that, you might want to shift to Newton. And that's what John does in his nested fixed point algebra. Okay, that was a lot of detail. So here's the Pauli algorithm. It is start with successive approximations, switch to Newton whenever the relative tolerance is close to beta, and then you repeat until convergence. You know, you can always go back and do more successive approximation if this doesn't work. Then step 4, do analytical derivatives of the Bellman operator. So here's a Bellman equation in integrated value function space. I want to take the derivative of this guy. I need that to do the Newton-Kontorovich iteration, right? We need the derivative of the Bellman operator to do that. You might think, oh, this is difficult, right? No, it's not really, right? It's really just taking the derivative of this guy. And it turns out to be very, very simple. It's like beta times this guy here, right? Times the choice probabilities. You get like choice probability weighted derivatives. And this is really just the state transition matrix. That's one line of code in MATLAB. So it's not hard. Or Python. Okay, so here it is. Here's my MATLAB implementation. Value of function, the value of keeping, value of replacing. Okay, remember to do the recentering of the log sum. And then if I want to calculate the derivative of the Bellman operator, I just take beta times this discount, the discount factor times these transition matrices times the CCPs. This is a probability of keeping, this is probability of replacing. 1 minus probability of keeping. So pretty easy. And then you can go on and calculate more derivatives using implicit function theorems and whatnot. Okay. It's like mostly an appetizer for reading this original material by John. This is documentation manual because he's spelling it out. And there's limits on how much we can do in the time we have here. So I'm going to just fast forward to the last part of the CPR, right? That's the BHHH alpha. What is that? So here's Newton's Raphson's algorithm for searching over the parameter space, right? It's something with, like, you have some initial parameter vector, then there's a step size, then you're taking the inverse of the Hessian times the gradient. Okay. It's maximizing likelihood function. Now we have to recall we're doing maximum likelihood, right? So there's something called the information identity there. It's like the Hessian so the expectation of the Hessian is equal to the outer part of the scores. So why don't we just use that structure, given that this is maximum likelihood, and replace those second order derivatives by just taking the outer product of the scores, which is much easier because now you have to differentiate only once, right? Not twice. So there you go. Okay. Of course, it's only valid if the information identity holds. So that's at the true parameters. Model is well specified for n going to infinity and yada, yada, yada. Okay. Why is this smart? Baron Hausman did. Well, even if you were doing, say, Newton's method, you're kind of relying on your quadratic approximation of that function being a good approximation, which is probably a good approximation in this area of the function, right? It's nice and concave, and we take this area here, calculate the first and second order derivatives, use that to use your quadratic approximation. Let's say it goes like this. You take it to the top of that quadratic approximation. That's your standard Newton step. Now, if you were doing it down here, your quadratic approximation looks like this. Okay, maybe it looks like this. And it kind of takes you the wrong way. It takes you in the opposite direction of the gradient. Well, if you're using BHHH in this area, you're multiplying with the positive dividend matrix, even though the function is in the convex area of a likelihood function, because you're essentially taking the matrix squared, right? Can't be negative. So that's an additional advantage. As if you're in convex area of a likelihood function, you don't move the wrong way. Okay, so that's what Donald would say. That's the way to the top. Use the BHHH algorithm because it saves you computational time, right? Don't only have to do the first order derivatives and always move in the right direction of the gradient. Maybe you overstep a little bit, but then you just do a little bit of line switch. Okay, and then you get convergence. And look at the numbers. Here's the computer time. Now it's 0.08 second and not like 2 minutes, okay? Because we implemented all these different things with the nested fixed point algorithm. And if you don't believe me, let's get MATLAB started again. I think we're here, right? DSE1, run bus data. There you go. We're pretty much done, right? 0.08 seconds. Okay, because we did all these things that was written down in the manual. So read the manual. Implementation matters. I think that's all I have to say about that. Okay, yeah, we do a lot of comparisons, and essentially here is MPAC ample. It works most of the time. Computer times are similar to what they found. We speeded up a little bit, probably because we had a different computer, and but you do NFXP, it's roughly the same. Okay, so these are two nice ways of implementing structural estimation of an discrete choice. Okay, so I have 24 minutes to talk about this paper, which is more than enough if you're still awake. Okay? And I hope you're all. We're going to talk about cars. Okay, we're going to move to Denmark, where I'm from. Cars are very expensive. Okay? So this is a Volvo, old Volvo, XC70, of like the whole shebang with leather seats and everything, concert hall and the nice stuff. It's pretty expensive. This is like, I don't know, it's probably $1.5 million Hong Kong dollars, so it's pretty expensive. Or 200,000 American dollars. So that's, where's all that coming from? Because, you know, in America, you can get this almost for free, like $62,000. Okay, so what's going on? Well, we pay taxes, registration taxes, and I've learned that we are not the country with the highest registration taxes around. In Singapore, it's even more. Okay, but at least in Europe, we are #1. Okay, higher taxes. And this is like a little cheaper car, Toyota Avensis. And you see we're with the taxes at a pretty high level for essentially the registration taxes in the sample period was on the margin 180%. There's some deductions at the bottom, but then once you go to cars above like 100,000 kroner, then it's like 180%, and then you pay value-added tax, which is 25%. On top of that. So it's like we pay tax on the taxes. So that's pretty expensive, but we get a lot of stuff. We get like free education, you know, free hospitals, a bunch of stuff, of course, because it generates tax revenue. So it's like 2 to 3% of GDP and 47% of the total tax revenue, depending on, you know, if it's an upturn or a downturn. Because people tend to buy cars when, you know, our economy is booming. Most of that is coming from the registration taxes, and some of that is coming from like fuel taxes, which is not unusual high for Europe. We only like double the price at the pump. So it's like, you know, half of the price of the pump is taxes. Okay, so now what we want to ask here is, how to get more Volvos? Or, you know, what's the consequence of shifting cars, switching car taxes away from purchase to the usage, driving the cars instead of owning the cars, like gasoline taxes or road user charging. And so what we find, and that's kind of be the punchline of this paper, is we are over the top of the ladder. So what we do is we formulate a dynamic structural model, estimate on Danish register data, and then we calculate the Laffer curve by changing the registration taxes and also changing the fuel taxes at the same time. So it's like a two-dimensional ladder. Turns out that we can lower both of those taxes, or we can at least lower the registration tax and then get higher tax revenue. Okay, so here's the model. Okay, so we're going to talk about equilibrium trade in automobiles. So now it's a bunch of decision makers that are choosing different discrete choices. Now it's not just replace or not replace. It's like, what is the car you want? And cars are different. Okay, so you can have different cars that are different by the types, like makes and models. Okay, so you can have like Volvo and, you know, Toyota. And they're also different by the different age. So you can buy used cars. Okay. And then the consumers, they are making driving decisions. You need that in the model. Otherwise, it's hard to say anything about, changes on the driving margin when you're changing the gasoline tax. And they're making ownership decisions like purchase, replacement, trading, and scrapping decisions. They infinitely lived and maximize expected discounted utility. We're going to have extreme value shocks. So they're going to be generalized extreme value shocks because we have some kind of nested logic structure. And, which is new compared to what we just did, is we're going to have endogenous prices in equilibrium. All the used car prices is going to be endogenous. Okay, they're going to be those prices that match supply and demand. So we're going to try to impose that additional restriction. Okay, so here's the what we call the Doubly nested fixed point algorithm. The outer algorithm is the same. We maximize the likelihood function using BHHH. Okay, search over the parameter space. But every time we do that, we need to solve for the prices that clear the secondary market. And those constraints would be supply equal to demand for all the used cars of different types and different ages. Okay? Now, in order to figure out what that demand and supply is, you need to have a model for individuals' trading decisions that for a given price vector, you will have to solve single agent dynamic programming problems for given vector prices. Now, given that, you can compute the trading decision, how the musical chairs are changing, like you're selling a Volvo and someone has to buy it, right? So there's going to be a trade transition matrix is implied by the conditional choice probabilities of this model. And then given those trade transition matrices, we're going to do like John, finding the ergodic distribution to these trade transition matrices, okay? And they're going to be fixed points on those macro transition matrices or fixed points on these equations, like the ergodic distribution to this trading and aging matrices. And then that gives us essentially the excess demand. So you got quantities, which are now fixed functions of those prices you started with, and you got all the trading decisions, conditional choice probabilities derived up here. So let's see how far we get with that. That's 17 minutes. Okay. Okay, so that's the plan. That's the roadmap, right? Let's start simple. Just solve the single agent problem. Here's a single agent problem. So people, they get car utility, and the car utility, well, that depends on the choice. It depends on the age and the type of the car. So the car kind of delivers some car services, and there might be like a decreasing function of the age of the car. Okay, and maybe like Volvo XC90 gives like more utility than like a Fiat Punto, and kind of shift up that curve. Nothing wrong with a Fiat Punto, but there'll be differences across different groups. And then there's marginally sold money, and you have to like pay some operating cost and then some trade cost. Every time you buy a new car, you have to purchase a car. But if you have one already, you can sell the car, right? So there's going to be trade cost. And there may be some transactions cost because of like Lemon problems and whatnot. Maybe you're like deeply emotionally attached to the car, and there'll be also psychological transaction cost. Okay, so, and then we have like an extreme value shock. So they're going to be generalized extreme value. This is very hugely simplified. Just going to go through the choice tree here for a car owner. Okay, this is a car owner that choose between different options. Like either I keep the car I have, right? And I'm just going to have the same car tomorrow, it's just aged. Or I can replace it, and if I replace, I need to decide which car I want to buy, which one of those J different car types. And if I say go with car type number 1, I have to choose if it's a new one, a used one, and so on. And this is like this nesting structure of the choice tree. And you can also like we call it purge, like get rid of whatever car you have. In all those situations where you're getting rid of the existing car, except if you're keeping it, you also have the decision whether to scrap it or to sell it at the secondary market. Okay, so all these here ends with like a scrap sell choice. So you can see there's already kind of a lot of choices. And we're going to have for each of those choices, just like Harold Zucker, right, on steroids, we're going to have for all those choices, we're going to have choice-specific value function, just like we have already, right? Like, just like Harold Zucker had for keep and replace, we're going to have for keep and for purge. This is like purge, but if you purge, you also need to take the decision on how to get rid of the existing car. Like this is your sell scrap choice. And if you replace, well, you have to choose what kind of car you're replacing with. Is it like a Volvo, or is it a 5-year-old Volvo, or a 7-year-old Volvo? And what did to do with the old car? Okay. So all these, this is going to essentially give you the different choices. It's just a little bit more elaborate. Okay. And then there's going to be choice-specific value function. I'm not going to go through all of them, but let's just say here's one. This is if I wake up in the morning. This is my state, right? With a car type I, and it has HA. If I choose to purge it, what I'm going to have tomorrow, I'm going to have no car, right? So get the utility of no car because you just got rid of it. And then I get, because I chose to scrap it, that's this, then I get essentially the utility value of the scrap value of that car. And tomorrow, my expected value is, I'm going to be the expected value of having no car. So that's like the what we call the empty set. So you see, for all these different combinations of states and choices, it can be state and choice specific value functions. Okay? And they all depend on the current utilities and the future expected utilities. Here's another one. This is for keep, right? So if you keep, well, you're going to get the utility of the car that you have, like IA, and then with some probability falls into an accident, becomes a clunger, have to leave the market. But otherwise, you get the discounted expected value of the same car. It's just 1 year older, right? Okay. Or you can buy a car, for example, and not scrap it, sell it at the secondary market, and then you get the utility of the car that you bought, right? That JD car, that's your choice. But then you have to pay the trade cost, which is like the difference in the prices between the car you buy and the car that you own, and then potentially sell as transaction cost and buy as transaction cost. All that you can specify. Right? We're going to estimate the parameters of this model. Okay, so all that here has the expected value on the right-hand side, and I haven't told you how to calculate that. Well, do a little log sum. Well, it's going to be a nested log sum because we have the nested locus structure. I just wanted to like throw up the simple version here. Okay, and then you see expected value is a log sum of all those choice-specific value functions that you got right here. Okay, they have on the right-hand side all those EVs, right? So it's a mapping from expected values to expected values. And then you just do exactly like the nested fixed point manual, right? Find the fixed point there using a combination of successive approximations in Newton-Kantorovich iteration, very fast. Okay, the conditional choice probables, well, they're going to be logit or nested logit forms. And everything is nice and differentiable and smooth, and we can calculate analytical derivatives using implicit function theorems, just like John did in 1987. Okay, so that was the how to solve the fixed point problem. Okay, now given the fixed point problem, we can get these trading matrices. Okay. Okay, so first, let's just define what this Q vector is. That's a fraction of consumers holding cars of different types, right? And they're kind of lumped into different, vectors. Here's this car 1 and car 2, car J, and then there's also one for the no car. And of course, no car, it doesn't have an age. And then for car 1, you have essentially the the fraction of consumers who own car one of H1 and all the way up to H8 bar. Now this is like prior to the trading phase. So that's after your car is aged. So there's no cars that are 0 years old. No new cars in this distribution. That's just by our timing convention. So that's the ownership distribution. And we want to find that that distribution as the fixed point of that equation here. So what is this trading matrix? I'm not going to go into the details of it. It's just, I want to say it depends on all those conditional choice probabilities that we just calculated. Okay, so for example, here, this is the probability of keeping the car. Oh, this is the one. You can either, if you stay with the same type of car, it can either be because you kept that or because you bought that same type of car again. Okay, so anyway, the bottom line is this depends on the conditional choice probabilities we're already solved for. We can easily calculate this stuff. It's like just matrices. Okay, now that's a trade transition matrix. And then there's an aging transition matrix. And together, here's how the distribution is evolving. You wake up in the morning with looking at your car at time t. Then after the trading phase, there's going to be this post-trade distribution, and then after the aging, it's going to be all cars are going to be 1 year older. Okay, and the ergodic distribution we're looking for is that stationary distribution, which is the fixed point of that equation. So we can calculate that, and once we have that, we know the Qs, and then we can calculate supply and demand for cars. That here's the demand for vehicles of type J and HD. Well, what is that? This is the conditional choice probability. This is the probability that you're buying that, given that you're, for example, in a no-car state. And then you also have the probability of buying that car, the conditional choice probability, given that you're in some other state, okay? We're just aggregating over the distribution using that post-trade distribution, aggregating all the choices for the people who are taking the choice of that particular car. That's the demand, right? Demand is essentially if the probability of buying that car is high, well, demand is going to be high. And then so supply, how do we supply the cars to the secondary market? That's by selling the cars. So that's a fraction of owners that sell and not keep. This is the people who sell, right? That's people who are not keeping and not scrapping their cars, multiplied with how many people who owns it. Okay, so now you have like supply and demand, and both of these are functions of the prices because we solved that problem conditional on the price vector. Okay. So this is how you do it. And if you didn't get all the details, fortunately, we have code. And you might wonder, doesn't this take forever to, is Doubly enough to fix point algorithm? Let's just see how it goes. Let's see. Run estimation it's called, right? So if you want to try it out, you just go and do the estimation. Okay, it takes a little bit longer because it's a little bit bigger model. But it's kind of already taking some iterations here, improving the likelihood. Okay. First order optimality has to go to 0. Eventually it converges. Okay. Oh, here we have like, I don't know, 120 parameters. Okay. So that's why you want to use that's why you want to use the BHHH algorithm, right? Because now your Hessian suddenly becomes like 120 by 120. You do that numerically, and every time you need to kind of calculate fixed points. Good luck with that, right? So that's why we are calculating everything analytically and rely on the BHHH algorithm. So we only need the first order derivatives. Essentially, the computational time here becomes independent on number of parameters almost. Whereas before it was like quadratic in number of parameters. Okay, anyway, I think it's going somewhere. Let's just come back. I'm lacking time, but it'll plot out what the computational time is. Okay, so we can add some persistent consumer heterogeneity. There are going to be different types of consumers. This is John Rust. This is me. I'm buying his old Volvo. And you can see there's like lots of gains of trade here, right? Because both consumers are very happy. And my alternative would be I had no car. I was visiting John, and I was like rejected by the Mercedes because I didn't have a good FICO score. So I had to like go on the market, buy a used car from John, and he was kind enough to sell it on a really low price. Anyway, so here's a little example from this John and Bertel economy. This is John, that's a blue one, right? And I'm the red one. I'm the poor consumer from Denmark. And you see here's the probable, this is like this distribution, the post-trade distribution. And this is fractional consumers that are rich that buy the new cars. This is like John, right? And then out here, as the cars are getting older, you see more likely that Bertel gets a car. Now you increase the transactions cost. You see what happens? It disproportionately push the poor guys out of the market because it kind of closes down the secondary market. It just makes it too expensive for me to buy old Volvos because I couldn't get it at like John's parking price. But not only that, it also reduces John's probability of selling that car, right? Because, or buying a new car, right? Like getting this nice Volvo XC90. You know, that he was depending on getting rid of the old one, right? Otherwise, he would not have rooms in the garage, right? You see, there's always another car over there. Okay. Anyway, so you can, this is the kind of illustrations you can do. You can also estimate the model, and that's what we did. And I promised you to that it should converge at some point. Okay, yeah, there you go. These are all the parameters that we estimated. Okay. Okay, and well, you can try it out yourself. These are the parameters, and they're kind of significant. We have lots of data. And here's the computer time. It took like 1.5 minutes. Okay, so that's okay. Yeah. 49 million observations. But what we do is we discretize the whole thing, and then we calculate the conditional choice probabilities or the state transitions up front in kind of cell-based, almost cell-based like that. So we don't have to like do that some all the time. Anyway, the data goes with it, this tabulated data. Here's a little bit of model fit. Model captures the kind of boring things that like poor households are buying more crappier car and stuff like that, right? So I'm not going to go through that. It predicts the market shares of the different types of cars. Also across, here's a choice probabilities for the data is a blue one, right? Or for aggregated over different types of cars. And so here's new cars and different used cars at different ages. Here's a sorting of different types of consumers into different car types, or into different types of consumers, that's the different colors, into different car types and ages. And you got the age here. This is like 25 years old. Out here, it's like a new car. Okay, and this is like different types of car. This is like no car. Okay, so it's like light brown, light green, like more environmental cars, like more heavy brown car, like a I don't know, like a Hummer or something. We don't have many Hummers in Denmark, but you'll see the sorting. This is what we see in the data. Okay, and so here's like, this is like a long work distance, poor consumer and a rich consumer. So this is like me and John. Okay, you see in the data, it's also like, you know, poor economists buying the older, crappier. And you can also see how that changes. Now the question is, can the model replicate that? Yes, it does. Beautiful. I love it. Okay, here's the sorting also in, yeah, it's just a different way of looking at the same. Here's the predicted equilibrium prices of the secondary market. They kind of capture what we observe in the data. We do a counterfactual. I'm just gonna, refer the reader to the counterfactual here that we are doing, but let's look at the Laffer curve before we start. Okay, I have 16 seconds, so let's just borrow 1 minute. Okay, so here's a Laffer curve. I got the fuel tax here. Okay. And then you got the car tax here, the registration tax. And this is where we are today. Like that's where we are today. So you can see if you are, look at, here's we are reducing the registration tax. If you're going that direction, you can get higher tax revenue. Okay. Yeah, way above the top of the Laffer curve. Okay. And you can also, if you both reduce that registration tax and increase the fuel tax, you get even higher. And that's the outcome you're proposing to the Danish government. Tax the cars a little bit less, but get the money back on road user charging or higher fuel taxes. And what do you get out of that? You can also calculate CO2 emissions from all that gasoline, okay? And of course, it's going to increase if you are reducing the fuel taxes and reducing the fuel taxes and the car taxes, then people have more cars and drive them more, right? So of course, it's just unitarily going to increase the CO2 emissions. It also increases welfare because people get utility, okay? But if you add these together, because this enters negatively into the social welfare function, and calculate the welfare, you can find depending on how much what the price of CO2 is, you can calculate where the welfare max is in this function with this model. Here's the revenue max. Gotta increase the fuel tax, and you gotta reduce the registration tax. That gives higher taxes, but it also gives, so this is like the contour curves of those graphs here, like the Laffer curve here. Okay, so within this area here, you get higher taxes, right? With the yellow one. Here you got welfare, right? So if you decrease the taxes, consumers are going to be happier. You get higher welfare down here, consumer welfare, but you're also going to get higher CO2 emissions, except in this area here, above this curve. So there's a sweet spot where you both get higher consumer welfare, lower CO2, and higher registration and higher tax revenue. What's not to like? Okay, that's a green area. And depending on how you weight these different objectives, you're gonna get to different results. Anyway, I'm over time, so I'm gonna stop here. Let's take a break.